Okay, good morning again, and welcome to this morning's panel on quantum technology for maritime dominance. Hey, what a great conference this has been so far, AFCEA and the U.S. Naval Institute. I haven't been to an AFCEA West. My last one was about 2003. So back then it was incredible, and what folks have done with it has made it even bigger and better, so it's really wonderful. I'd like to thank AFCEA International, U.S. Naval Institute, and IBM for sponsoring this very important forward-looking panel. And if you look at it, it's very consistent with the theme, our acquisition and readiness, on pace to meet global security demands. I'm going to talk about that a little bit as I open up. Again, my name is Vic Mercado. I will be your moderator this morning. We have Tim here to help facilitate questions. There's Tim back there. Okay, the first order of business, I would like to introduce a very distinguished panel to my left. Very distinguished. First, Captain Jesse Black, right here to my left, the commanding officer of the U.S. Naval Research Laboratory, who left cold D.C. to spend time with us today. So welcome, Jesse. Captain Black is from South Florida, as a distinguished surface warfare officer. You know, I have a soft spot for SWOs. I'm biased. And an engineering duty officer. As a SWO, he served on Cape St. George, the mighty Cape St. George, in multiple jobs in multiple departments. He and I were talking about it earlier, over a 4-year tour that included a surge deployment for Operation Iraqi Freedom. As an engineering duty officer, he served in the most challenging positions with PEO carriers, NAVSEA, our shipyards, DDG 1000, solving Navy's most complex engineering challenges. And these challenges, I'll give you an example: Gerald Ford weapons elevators, nuclear refueling overhauls, and integrated power and propulsion systems on Zumwalt DDG 1000. Really significant challenges. He also served in the White House as Senior Sustainability Officer under 2 administrations. He has a Bachelor of Science in Civil Engineering from the University of Idaho and a Master of Science in Electrical Engineering from the Naval Postgraduate School, which is my alma mater as well. Next, over at the far end there is Mr. Michael Spock McMillan. He is the Executive Director for the Naval Information Warfare Center Pacific, where he leads more than 5,000 civilian and military personnel in research, development, and fielding and support of advanced C4ISR cyber and space capabilities. He is a former naval aviator. I respect the aviators too there, Spock. And a veteran of 42 combat missions in Desert Shield, Desert Storm, and Operation Southern Watch. He has a Bachelor of Science degree in Material Science from Rochester Institute of Technology and a Master's in National Security Affairs from the esteemed Naval Postgraduate School. Next to him is Dr. Dan Gunlicke. He's the Technical Director for the Naval Quantum Computing Office. He is also the Program Office for Nanoelectronics for the Office of Naval Research. Dr. Gunlicke received his doctorate from the University of Oxford in the UK for the theory of gated carbon nanotubes from quantum information processing. He is also a former Peter Mark Memorial Award winner for outstanding work by a young scientist or engineer. Lastly, but definitely not least, right over here is Dr. Joseph Brose, is the Vice President for Quantum Growth and Market Development for IBM. Dr. Brose is a leader in the development of workflow applications using quantum algorithms and leading policy efforts for IBM's regulatory export control. He has extensive experience with the U.S. government projects and has supported Defense Homeland Security and other departments and agencies through research, consulting, and fellowships. Dr. Brose served as a White House Fellow for the Office of Science and Technology Policy and is a British American Fellow at Johns Hopkins School of Advanced International Studies. He has a PhD in physics from the Swiss Federal Institute of Technology in Zurich and a Bachelor of Science in Physics from MIT. So as you can see, we have a lot of brain power on the stage to discuss this topic at hand. Okay, what I want to do is now just set the stage and provide a scene setter for what we're going to talk about today. And I guess, like I said, I think it's very consistent with the theme of this conference, or the pace to meet global security demands. And when you think about pace, it needs to be in relation to the competition, the global competition in this space. You know, I think when you heard Pappy, Admiral Paparo, talk about the pace, he said never be satisfied, you know, and I would say, you know, we have a competitor that is investing a lot of money in this space, and I'll talk about that a little later, but we need to maintain the advantage. So, from data compiled by the Quantum Insider, who really is passionate about compiling logistics globally, over 30 countries, including the EU, have active quantum programs. When you take into account both current projected investments that's consistent with their global or their national strategies, the investments total about $40 billion, if you think about that. Can anyone here guess who is the biggest spender? Who is the largest investor in quantum? China. And the number they are spending in public funds is $17 billion. Now you can look at, you know, type of investments, facilities, or science, but that's a significant commitment, all public money. Where do you think the U.S., what place is the U.S. in this global investment system? U.S. is about third. Some say we're fourth, okay, to the tune of about $3.9 billion. 17, 3.9. The UK is second with a little bit more. So I'm not a budgeteer or anything, but I like to follow the money. So from a commercial and industrial-based perspective, should we be concerned commercially? Maybe, maybe not. Yes, there's a lot of. What about from a national security and Department of Defense perspective? It's a good topic for the panel to discuss. Okay, last month, if you look globally, NATO just announced its quantum technology strategy. NATO has a strategy. U.S. is part of NATO for a quantum-ready alliance. The strategy is meant to lead the target in anticipation of international norms development, and I think this panel will do that too. Their strategy, the NATO strategy, discusses responsible innovation, a transatlantic quantum community, and protecting the alliance from the quantum threat. The strategy acknowledged, and I quote from the strategy, quantum technologies have a double-edged impact on cybersecurity, we may talk about that today, and defense, benefiting both the defensive as well as the offensive. Okay, for the Department of Defense, the Undersecretary of Defense for Research and Engineering has identified quantum as a critical technology, at least the last two administrations. They identified defense applications like atomic clocks, quantum sensors, quantum computer, and quantum networks and communications. And some people argue that China is a leader in quantum networks and communications. Think about that for a second. The newly informed DoD Office of Strategic Capital identifies quantum as a critical technology that needs additional capital for national security. Again, I say follow the money. Now, Navy hasn't stood still, so back in February 2022, Navy stood up the Naval Quantum Computing Program Office, led by NRL, and Naval Information Warfare Pacific, which includes Naval Warfare Center subject matter experts. The 2024 NDAA, for reference, authorized increased funding for a distributed quantum network testbed, development of a next-generation ion trap computer at the Air Force Research laboratory. And I asked Captain, how come it's not at Navy? Or maybe Navy needs its own computer. We can talk about that. Directs the Secretary of Defense and the Undersecretary of Defense for Research and Engineering to submit a report on the feasibility and advisability of establishing a quantum computing innovation center within the Department of Defense, and this report is due by November 2024 this year. The most recent DoD budget request includes $75 million to accelerate quantum technology. Again, follow the money. During my time in OSD, I worked closely with DARPA, and I fully understand the challenge of transitioning R&D to service programs and ultimately fielding capabilities. This is not a new problem, as we all know. The recent Commission on Defense Innovation Adaptation final report, this was sponsored by the Atlantic Council, states, and I'll quote from that report, "The United States does not have an innovation problem, but rather an innovation adoption problem." That is to say, the U.S. leads in many emerging technologies relative to defense and security, from artificial intelligence and directed energy to quantum information technology and beyond, but the DoD struggles to identify, adopt, integrate, and field these technologies in military applications. That sound familiar? To enable a leap ahead in capability, as USDRNE said, on a number of fronts, and when I think about a number of fronts, I think about all domain operations and all of the tenets of the joint warfighting concept, which was developed over the past couple of years. And those tenets are, as we recall, FIRES, Joint All-Domain Command and Control, Information Advantage and Contested Logistics. DoD and Navy need a plan, and I believe they do, to aggressively leverage the quantum advances in the private sector today with a roadmap, I like that term, to some measure of organic capability, and I think the Navy is all about organic capability, to develop distributed maritime operations at both the fleet and potentially the carrier strike group levels. Okay, so with that, I want to now turn to the panel so each of these members can give their opening remarks. And what I thought would be beneficial for first Dr. Brose to give, as the private sector representative, to give his perspective, the industry perspective on what industry is doing. And I can say, you know, I painted a little bit of concern with regard to some of the investments in public funding, but I can tell you in no uncertain terms, and I had a discussion again with Admiral Paparo, that the U.S. is the leader in this technology by years, okay? But we can't sit on our laurels. But it's important to understand what the private sector is doing in this area. And after that, we'll give the other members of Navy Research Lab and folks to show what they are doing. And then we have the advantage of having the CO here to give even the broader perspective. And then we will go into Q&A if that's okay. So Dr. Brose, please.
Great. Well, thank you, Vic. And let me just do a quick sound check. That handsome fellow in the back row back there, can you hear me? Okay, thank you very much. Listen, Vic, thank you for putting this panel together. Thank you to the other panelists here. This is quite an assembled group. I want to focus my remarks on quantum computing. I don't mean to give short shrift to quantum sensing and communications, particularly when it comes to PNT applications. Those are extremely important and probably right now in the quantum sphere leading in terms of their fieldability. So, but IBM is a quantum computing company. It is a computing company, and I want to limit my comments to those at the moment. Vic mentioned that the United States is third or fourth in terms of the funding race. What I'll add to his comments is that we share that bottom quartile with 9 other nations. Most of them are allies. So we're not only underfunding quantum, but we're underfunding it across a huge footprint of the globe with public funds. IBM is a private company. We do not rely on the federal government to develop our program. So the remarks you're going to hear today are really those of IBM and our program. But before I start, I would also like to, right from the outset, acknowledge the great leadership we have seen from the Navy and from Air Force Research Lab in quantum computing. They truly are the leading lights, not only in DoD, but really in the entire United States government, along with the Department of Energy. Those are the two that are really embracing quantum computing. So let me talk about IBM. We have a roadmap. We're not secret with our roadmap. It's quite public. And let me give you the bottom line up front. We fully intend to field a 100,000 qubit machine by the year 2033. In fact, we will field 3 of them. We have already partnered with the University of Chicago and the University of Tokyo for 2 of those machines. To give you some perspective of the capacity of these machines, a 100 qubit machine has computational space and dimension that is larger than all the atoms in the known universe. So you can imagine the computational power behind a 100,000 qubit machine, which will correspond to about 2,000 logical qubits and 1 billion gate operations in that capacity. The use cases are something that we'll go into a little bit, but they have definite military, definite defense impact to them. We have built an ecosystem globally, and we already have 9 machines deployed around the globe. We have 38 quantum information centers around the globe. We have 250 partners around the globe. These are large companies. They are companies like JP Morgan Chase, Exxon Mobil, British Petroleum, Boeing. We have 250 members of our quantum network. We have educated over 8.5 million learners that have taken at least 1 course in our software called Qiskit, and we have 500,000 regular users, including those from the Navy and Air Force, on our system. The IBM is planning a sequence of machines moving to 1,000 qubits, which we announced this last year, to 10,000 qubits, to the 100,000 qubit machine by 2033. Our opinion is that whether it's an IBM machine or not, the Department of Defense should have access to the best quantum system available to it. Those are here in the United States. But I'm also, at the same time, going to say that Germany and Japan right now have better quantum machines than any owned by our federal government, and IBM sold it to them. So there are allies, and they are important allies, and they are important partners, but we are really wanting the United States government, and particularly the Department of Defense, to embrace the quantum computing discipline, to fund and acquire the best available equipment. And if it turns out to be one of our competitors, so be it. I feel like IBM can compete head-to-head on any playing field. I'll close with my opening remarks by saying DoD generally, and I've been recently told, procures against capability gaps. And that makes a lot of sense. Quantum has yet to show that it fills a capability gap. But one of the ways that it will demonstrate that capability is by the Department of Defense investing in the workforce and the machines, the people, and doing the algorithm development for those applications that are uniquely defense-related, and then that gap will be shown to be filled. If we wait for spin-in to defense from the commercial sector, we're going to be waiting a much longer time than we probably should, given the climate and environment in the world. I'll close my opening remarks there. Thank you.
Okay, thanks, Dr. Brose. Now, Dr. Gunlicki, please.
All right. Thank you, Honorable Mercado, and the distinguished guest here on this panel. Before I start with my opening remarks, I also want to mention that unlike the other people representing the Navy here, I'm in the Navy by marriage, and San Diego is a special place for me because after I left the UK, my wife, who also was a Naval Academy graduate, went on her first tour on the USS Lassen, and it was on its maiden tour in the Pacific, and came back here to San Diego. So I got the opportunity to spend some time here in San Diego, and I'm happy to be here again. It's a wonderful place. So going to my opening remarks. So I'm representing the Office of Naval Research on this panel here. So I'm going to make a few remarks there. So the Office of Naval Research is preparing for quantum to come to the Navy, and are looking for ways to get these applications into the fleet. We are working with the Office of the Undersecretary of Defense for R&E, specifically the Director for Quantum Science, Dr. John Burke. So we have a coordinated roadmap together with John Burke. So some of the things that happen at ONR and some of the work that they're supporting there is in quantum sensors, where they have demonstrated in 2023 a new way to measure actually small variations in the local gravity, and they can correlate that with gravity maps taken from satellites, and using this information they can get better precision on the position that our vessels are at. So that's one example where we have already taken quantum technology, and it's actually being tested on ships right now. But I'm also going to talk more about quantum computing, because that's my own background. So I'm a scientist at NRL. My commanding officer is sitting here right next to me, so I better not say anything offensive. In quantum computing, there is, as Dr. Brose just pointed out, an enormous opportunity. The amount of information that is contained in these quantum computers is gigantic. And we already heard that if you want to somehow represent this information, already on the computers that IBM has today, you need more information than the number of atoms in the universe. So that shows you the capability is in there. Now the challenge is that to manipulate these states and making a useful application out of it, you have to do that with a relatively small number of gate operations and measurements. And that task isn't trivial, because when it comes to quantum computing, we have to think in a new way. And we have this exponentially large space, but we still have only a relatively small number of circuits that we can execute. So that requires very careful planning when we develop our applications. I'm happy to sit here with my colleagues here because to make this a success, we really need this public-private partnership because we currently are not in a position to do what IBM, IonQ, and other companies have already been able to achieve. So when I started to work at NRL in this area, it was in 2018. It was on the recommendation of our NRL Director of Research, Dr. Danley. And he specifically said that we should be focusing on developing algorithms and applications for the Navy and then partner with public companies to provide the best possible access. And if we combine the two, we will be able to have the edge. So that is our goal, but we are expanding our efforts at NRL, and the new Naval Quantum Computing Program Office is evidence of that. So in 2018, we worked with IBM to set in motion this partnership, and we had the plan lined out to get access to the Navy. Now, as it turns out, ultimately the hub was started by the Air Force through AFRL, and the reason for that was that we did not have our sponsors lined up on the Navy side. So the center for the DoD Quantum Computing Hub actually went from the Navy to the Air Force as a result of that. So the sponsor side is important for us. But nevertheless, we got a good deal out of this where we could get access to our Navy scientists. Now that was only restricted to NRL initially. So we had this challenge where we have all these warfare centers out there, and we absolutely need to get that access to the warfare centers. And that's where Dr. Petrzinski, who sits in the audience here, put in a heroic effort to try to get this deal broadened so that we can include the warfare centers. And that got completed at the end of 2022. So now anyone out there in the warfare centers, if you have scientists who would like to develop applications, you should be reaching out to myself and Joanna. So with that, I close my opening remarks.
Thank you, Dr. Gudnicki. Spock, Mr. McMillan, over to you, sir.
Okay, can everybody hear me okay? Thank you. Good morning, everybody. And first of all, happy Valentine's Day. So it's not too late. You can still send that text, send that special email, maybe order some flowers, or do something. Let me tell you, though, that if you don't do any of those things to whoever your significant partner is that matters to, going back and saying, hey, sorry about that, but I attended this great quantum panel at AFCEA, is not going to fly. It's not going to get you anywhere. So that's my opening statement. I do have a little bit more. I'm honored to be on this panel with such distinguished panelists and panel members. I am the least distinguished of this group by far. You've probably heard relative to quantum that there are people who know quantum and people who don't know quantum, and then people who both know and don't know quantum. I'm very much in the second category. Everything that I'm going to say about quantum, that I know about quantum, you're going to hear in the next 40 minutes on this panel, and it's mostly thanks to Dr. Petrzinski, who's sitting in the third row right there and educating me in the past 3 weeks. That being said, though, I do represent an organization, Naval Information Warfare Center Pacific, that does have people that know quantum and that have been engaged in quantum from its nascent and earliest stages. So from the early 2000s, when quantum was just kind of beginning and that term was just being thrown out there, we had scientists at NIWC Pacific who demonstrated secure communications through entangled photons. Since then, we've been involved in a myriad of other projects along the way, which we'll talk to a little bit about how projects like that evolve and how they need to grow and expand. including work with AFRL, for example, more recently, on testing the survivability of quantum communications equipment by using high-altitude balloons. Once quantum computing became a little bit more easily accessible to the average scientists and engineers like ourselves who could access it, we very quickly set about to map the Navy's problems to quantum capabilities. And that's, again, across the spectrum that we've talked about of computing, of sensing, of communications, and materials. And it's both the map of where quantum is obviously currently and where it is going. And that's the tricky part, right? Because this is like AI and ML, it's kind of the same thing with autonomy. You know, it's a sliding scale. So you're constantly measuring yourself and what you can do and what the problem set is to a space that is changing rapidly and is advancing rapidly. Where we are right now, I think computing and communications seem to be the areas in quantum that we are most advanced at. And so in that mapping, I think one of the real problem sets we have was stated by Admiral Paparo in his keynote, but I would differ with him a little bit, because one of the things he said was, you know, you can't solve the problems of food, fuel, ammo, medical requirements, and material movement with an app. And I would caveat that a little bit, and I would say that is the strength of quantum, and certainly quantum computing. Where we're at right now, the thing that we have most ability to do is to solve the very kinds of optimization problems presented by the movement of food, fuel, ammunition, and material supplies in a contested environment. Are we going to have a quantum computer on everybody's desk? Is quantum going to replace the systems we have right now on ships? I don't think we're at that point. I think we're probably a decade away from anything like that. But we have reach-back resources and compute resources that we can use to solve a lot of the Navy's optimization problems, and we can do that today with the right employment and the right application of resources to those issues and those problems. And Navic Pacific, we're engaged in that very heavily with these partnerships that we're engaged in, and we really appreciate that partnership with the folks that are around this table, on this panel, and their organizations, because that's what's making all of this possible for us. We're continuing to advance our work. We have probably a couple dozen projects in the quantum area, again, mostly spread out pretty equally along those 4 areas of communications, computing, sensing, and materials. But one of the things you have to realize is, like NRL, we're a Navy laboratory, we're a working capital fund. We do not have our own resources, or fairly limited amounts of resources, and we're not given millions of dollars by the federal government to go and do research in areas and develop things. You know, we do have Naval Innovative Science and Engineering, NICE funding, that is basically a small percentage of the money that we are paid for to do other work. We can take out and do things that we think are in the best interests of the Navy and Department of Defense and work on those research efforts ourselves. And that's really where most of our quantum engagement has come from. So the talk about sponsorship, I mean, the difficulty with, you know, our foe, with our potential adversary of China, is their ability to put resources directly to something like this that they recognize as important, and the fact that most of their research organizations are working directly for the PRC and therefore for the, you know, the Chinese military and the Chinese Department of Defense, right? We have all these spread out resources. We do not have the ability to put them all together collectively under a single banner with the kind of funding where then the innovation, as was highlighted earlier, goes directly into a capability that can be fielded. And that's really something we're missing, and something we desperately have to undertake. And so I look forward to the partnership with, and hearing and learning more from the folks at this table about how we do that more effectively. But at Navic Pacific, we stand ready, a ready partner to help you in that effort and to bring these capabilities into the forefront of naval application. Thank you.
Hey, thanks, Spock. Well said. Captain
right.
Black.
So I'm going to kind of wrap everything up here from my perspective. First off, thank you so much for being here today. Thanks for FCO West and my distinguished panel here. It's an absolute privilege and privilege to be up here today. So let's go back to the CNO's comments yesterday and talking about the 3 priorities that she's given us and the direction where we're going. We're talking about war fighting, we talk about the war fighter, and we talk about the foundation. And it's talking about the decision superiority that we need to be able to bring to them. And that war fighting capability, as we watch and what's happening in our environments and how fast they're changing, this is going to be one of those tools that will come to bear and will give us decision superiority. So there's the reason why, for sure, in that context. And it's about those warfighters having that advantage over their adversaries to be into that arena for what they need to go do. And the foundation comes back into is it's not just a single entity that's going to go do this. It's this combination, collaboration amongst all of us that continues to make these things happen. It's been part of our history, part of our trajectory that we've always been on. It will be what we do. Now, can we accelerate? Absolutely, and that'll be a big direction that we will go back and look to focus on. The Naval Research Lab, as she was talking yesterday, and we've heard other leaders talk in here, we resonate with all those aspects. And it's really cool because you talk about the pointy end of the spear and you talk about the warfighters. Well, that spear has a lot of other things that happen all the way to the other end. And it does come back into that basic and applied research and investing early on. And that's what the Naval Research Lab has been doing. Part of the reason why we haven't bought a quantum computer yet, because a lot of advancements have been made. But coming back to we have to have an understanding and purpose of how this is going to fit into our ecosystem. What are we going to do with this? It's just not that you have this ability to do this massive compute. As Dr. Gunlicki was talking, it's a very complex environment to figure out how to make it work and make it be instrumental in our machine that we run and with what we do. So Dr. Adam Black, a really cool doctor at the lab, really cool name. He put it really well when we had Dr. Gunlicki with some congressionals. What is the so what in this quantum realm with what we come back to? And I want to kind of maybe shed a little bit of light on that one from my perspective. If you look at quantum mechanics, it's the purity of where we're at. In the early, late 1800s and the early 1900s, we were able to make predictions. Scientists in our laboratories were able to make predictions that we're still proving out today because of the purity of what happens at the quantum realm. It's that pure. Quantum sensing, it's that pure at that sort of such a small level there that you can get so accurate with what you've got. You have purity of understanding where things are at. And for me as an operator, I'm like, okay, for a sensor, I can get to that level there. I never have drift on a sensor. I never have to recalibrate it. And I know purity is pure. That means a lot to me. That's incredible aspects. So there's the reasons and why and purpose of what we're driving to. In the quantum computing realm here, we've talked about this one here. For me, I see it as a new tool to our table, right? It's not necessarily going to replace the tools that we already have. I still use a calculator on my desk to do quick math. I open up Excel to do certain things. It's having that right tool for the right job to go do what you need to do. And the quantum computer is going to be able to do that one for us in a whole other regime. So I want to make sure that that's known, that people are understanding that it's not necessarily a replacement. It's a whole new, brand new tool to us that's going to open up things for us. So my final comments to this one is I look at the purity of our scientists. We talk about this one often. It comes down to the basics: physics, math, chemistry. These scientists have been charging up the hill for a very long time. And what's amazing to them, and we just got done with 168 proposals on new sciences that they're coming our way, the purity of that's there, but they have new tools now that are going to go and unlock things that have never been unlocked. We have a chemical equation in corrosion right now that they're looking to unlock. They said it was not going to be solvable in our time frame. They're now looking at it as an attractive way to come out. I think that we can go get this. So that's what the potential is in front of us here today. I look forward to the questions and continuing the dialogue. So thank you very much.
Hey, thanks, Jesse. Thanks very much. Okay, that's a great series of opening remarks. Now I want to start off, I want to structure the discussion for today. First, use cases, some of the specifics. What can quantum do for us right now, and then maybe look at the trajectory in the future. And I'm going to steal a use case that I learned in preparing for this panel. And I was made aware of Exxon, right? Exxon has 500 liquid natural gas tankers. And they do thousands of trips across the globe, dealing with weather, all kinds of environments. And it's back to optimization that Mr. McMillan talked about. So in order to do their mission efficiently, they've used a combination of classical and quantum computing. Now, let's overlay a military application. Everybody talks about and rallies around, I talked about the joint tenets of the joint warfighting concept, contested logistics. So think about a problem set across the Pacific in a contested environment where you're moving logistics by sea, by air. Maybe some of that logistics comes from additive manufacturing. Maybe there is damage. There may be areas where they need to be escorted. That problem to me is exponentially more challenging than just 5 LNG tankers moving gas across the ocean. So the question is now, it is the only way to achieve contested logistics, it's to take advantage of quantum computing to some degree. So that is just an application that I came across as I prepped for this, and how, quantum is absolutely critical to leverage what we have in the private sector for military application. And historically, like I said, we are very bad at it because we would like somebody else to pay for it until the very last possible moment. So let me turn it over to first Dr. Brose in the private sector. Any use cases that you are working with that in the public sector that probably has application, say, for the Defense Department?
Yes, in terms of commercial applications that could find traction in defense and in national security, the first thing to realize is, there are a large number of them. For example, you mentioned optimization, logistics, contested logistics. Also in the materials and chemistry areas, many of the companies that we work with, such as Boeing, we are utilizing quantum computing to optimize ply composites for aircraft and on airfoils. That turns out to be a very difficult problem. When you look at optimizing those materials against the various constraints of yield, modulus, weight, curvature, and various tensile strengths in 3 dimensions, that turns out to be a very difficult problem. They have successfully applied quantum computing to optimizing the development of those materials. When you translate some of those applications over to defense applications, a couple of things jump out. In the commercial world, we assume a certain level of stability to our markets, to our economy. In defense applications, one has to assume almost continuous threat. That means that the way these applications are developed and the underlying assumptions are often radically different. So while we can template certain algorithms and applications from the commercial centers and bring them into defense applications, we also have to be mindful of the underlying assumptions. Another one in the commercial sector is simply consequence management. The consequences of making a mistake in the commercial world might be a missed quarter or a lost job. In the defense area, it's lives. And it is a very difficult thing to understand the radically orders of magnitude difference between those 2 scenarios. So yes, we have a number of applications and use cases we are developing in material science, optimization, logistics, also in cryptography. And those are very important use cases that can template. But again, I want to urge that the Department of Defense has a unique set of assumptions and needs and capabilities, and in order to develop those in a robust way to account for the different levels of assumption and how they differ from the commercial sector, the DoD itself needs to build a workforce and a workforce with capabilities around quantum compute, like it has in quantum PNT and quantum communications.
Okay, so let me go over to Mr. McMillan here because you talked about mapping Navy problems, so I think you're dealing with probably specific use cases where quantum can help the Navy's mission.
Yeah, so I would like to address, though, what you just said about education and building a quantum workforce, and that is very true, and that is something we're also engaged in nascent stages. Again, in partnership with folks like IBM. I know you have your summer school that we've had folks attend. We've done at NIWC Pacific our own essentially Quantum 101, where we had more than 40 folks from other Navy labs as well come and receive some basic quantum physics training from professors at NPS, for example. And so we're trying to in the early stages, build what you were talking about. Because as many of you probably know, most quantum experts at this point are physicists. And so we have to expand that to a greater element of the workforce of other scientists, other mathematicians, other engineers, so they understand it well. To the use case, I totally agree with you, obviously, about the complexity of the DoD's problems. But at the same time, I don't want to overcomplicate it. You know, some of our problems in terms of things like, we talk about logistics, but even in terms of sensing, for example, and trying to determine what is the best resource or the best particular capability you have on site at any given time to be able to sense something, right, and then make that available to the larger network, is not that different a problem than a lot of commercial problems. And like one of our really smart folks at NIWC Pacific, who's working on a lot of the autonomy work, actually uses Uber Eats as a great example. And I think it actually really is a good example, because when you think about what somebody who's delivering that has to do, and if their system is optimized, they're on their way somewhere, they're bringing somebody's lunch, they've just picked it up at a restaurant, they're driving past a 7-Eleven. In optimization, effective optimization, if somebody then calls in, hey, I need a Slurpee, you would not assign that to somebody new. You would assign that to the person who's about to drive by the 7-Eleven, who can just pull in and stop, pick that up, and deliver that Slurpee to someone, and then the lunch to the place it was destined to go to. If you think about that in very simple terms and expand that into an area like the Pacific, whether you're dealing with a surveillance problem, or whether you're dealing with what are the right weapons to apply to specific targets to optimize the effects given the limited weapons we have to employ. You know, there are ways to bring this down, really specific naval and DoD problems, to bring this down to levels that we can understand, that I think we could apply quantum to right now today to optimize our solutions in that battle space.
Excellent. Now I'll open it up to either to Dr. Gunlicki or Captain Black. Anything to add? Go ahead, Dr. Gunlicki.
All right, thank you. I appreciate this discussion about use cases, because that is what we are all looking for. So our team has worked in multiple areas. It could be quantum chemistry, quantum materials, and that is one area that we consider fairly short-term relative to some of the other applications. And one of the things I want you to understand in the audience here is that when we talk about doing quantum computing, it's not all done by the quantum computer and the quantum computer spits out this magical solution. It fits into a bigger picture. So we have been working on corrosion and doing quantum chemical simulations using quantum computers that could reduce the amount of corrosion. At least we hope that it will. And we do this at atomic level. But that information, I was trained in quantum computing. I'm not an expert on corrosion. I know a bit about it, but we have a branch at NRL who have researched corrosion for a long, long time. So a lot of the challenge is a networking challenge. We have to pair up the experts on the application area with the quantum computer experts. And that's why the research that we do at NRL and the warfare centers is so essential. Another example is in satellite scheduling. So we have a project where we are taking information that we are getting from that relates to how we schedule the satellites and what targets they should focus on. It turns out that that is what's known as an NP-hard problem, where it could benefit from a quantum computer. And we have already made some good progress. And the reason for that is that we have been able to team up experts in quantum computing with the experts in that particular application area. And that is how we develop good use cases. Now, we have to just expand this effort into new areas. And I think that's going to be the challenge going forward, because once we get to the type of quantum computers that my colleague here described, the number of application areas is just going to grow, possibly exponentially, if I might suggest that. So we just need to respond accordingly.
Yeah, thank you very much. I've been reminded that we only have 10 minutes left in this panel, so to manage the time, if anybody has any questions, please come forward. But I want to give Captain Black to finish the discussion on use cases. Then I want to take a step backward and talk about trajectory. Is the Navy positioned properly, for the foreseeable future to take advantage of all the advances in in the private sector, and maybe get also Dr. Brose to talk about that too. So let's, if you would, Captain Black, talk about the use case pieces, and then we'll go from there.
Okay, yep, Dr. Gunlicki was exactly right with it, with a couple of projects that we have that we funded through our basics science to show what the use case is capable of doing. And we do see once that happens, it's really going to open up the door for more and more activity. As much as our counterparts here are continuing to climb the journey towards the more ability to compute, this sort of wonderful marriage that's happening as we move across is happening. So we're very data rich. Quantum computers are really great at taking large amounts of data and deducing down into relevant information that's important to us. So you can think about any paradigm that you have. For me, on a shipboard side of the house, sensors are cheap. We put a lot of them on there. It's very difficult for us to discern exactly what's happening. We're getting good at it, but a technology like this one would just be absolutely tremendous.
Okay, it's wonderful. Now, before we get into does Jesse think that the Navy is positioned well, I want to talk about one other use case, because we talked a little bit about quantum sensing and the ability to navigate in a GPS-denied environment. So think joint all-domain command and control, operating, at the edge, distributed maritime operations, not dependent on GPS, which could be denied, and to be able to sense and also close kill chains. Wouldn't that be a tremendous capability that Navy would need to execute distributed maritime operations? So I'll leave that with the last kind of use case that comes to mind for me. So let me turn over the question for Captain Black about, is the Navy positioned now for the future? And if not so, what do they need? What do you need? Go ahead, Captain Black.
Yeah, I would say we're very well positioned. We've taken 30 years of development in the quantum regime. We're watching the technologies mature with the companies. We're well paired with them. We have incredible institutions that we're laying groundwork on now today. Great collaborations with the Air Force Research Lab through our warfare centers. Everything is positioned well, and activities are well underway. Now, with that being said, do I wish we were going faster? Always, yes, and for sure. Am I a little bit worried about our counterparts? Very much so, which means we got to keep after it, but we got to produce results, right? We can't just have an idea here and run with it. That's what's the demand signal comes to us. We need to answer the call to make sure that this is going to be the right fit. So I do think we're well positioned, but could go faster.
Okay. So now that's the Navy's perspective. From the industry's perspective, is Navy positioned well from your standpoint? And what needs to be done in this relationship to make sure that happens, to enable us to maintain an advantage?
Sure. So, as I mentioned in my opening remarks, I really have to acknowledge and we greatly appreciate the leadership of both the Navy and AFRL in the quantum space. And also, I don't want to leave the Army out of this. What they've done in Rydberg atoms and sensing is also terrific at ARL. They're really the leading lights in the government along with the Department of Energy. Is the Navy well positioned for the future? Yes and no. Yes, as Captain Black mentioned, I think all of those are very strong facts. The no comes down to the workforce. Let me just outline what I call the tyranny of twos, all right? So there are about 200 degree granting institutions in the United States in physics for PhDs in physics. The United States graduates about 2,000 PhDs in physics annually. About half of those are foreign national, so that leaves 1,000. About half of those are in fields that are relevant to quantum information science, i.e. not geophysics or something. Of that leaves 250, about half of whom will go to Wall Street and be quants, leaving 125, and about half of those individuals will want to carry a clearance and live a lifestyle that requires, that is required by clearances, leaving about 75 that then need to go, and about half of those will become subject matter experts in fields that will then map, like corrosion or chemistry or materials, onto quantum. So you can see that it is a daunting thing to build a workforce, and right now, the Department of Energy and the QEDC consortium publish job openings. There are about 1,300 job openings for that small number of individuals. It grows about 100 every single month. So it'll give you an idea of the size of this quantum community. There are about 6,000 people, we estimate, who draw a paycheck because of quantum, computing, sensing, or comms. And there are probably around, we're estimating, 10,000 people globally who draw a paycheck as a result of quantum and quantum computing efforts, research and development. So I wanted to just lay out the tyranny of twos and the fact that building a workforce, I do not envy these gentlemen to my left and right. We have our own problems in the private sector, but they have a much even more difficult problem.
Thanks, Dr. Brose. Well, I mean, how time flies. We are about at the end of this panel discussion, and I think I could go on. But this is an important topic, I think, because it goes to the ability to really deliver maritime dominance, okay? And the pace is important, but the pace is relative, okay? To answer the question from the theme of the conference, are acquisition and readiness on pace to meet global security demands, in this case in quantum? I think the answer is yes, but. So going forward, I think we need to continue to discuss this and follow the money. So anyways, please join me in a round of applause for our panelists, and thank you for attending.